Definition of zinc ore deposits. Zinc ore deposits refer to geological formations or concentrations of minerals containing significant amounts of zinc, typically occurring in the Earth's crust. These deposits are vital sources for the extraction of zinc, a metallic element with various industrial applications. Zinc ore deposits can manifest in several geological settings, including sedimentary, volcanic, hydrothermal, and metamorphic environments. Sedimentary deposits, for instance, often occur as layers or beds within sedimentary rocks such as limestone, dolomite, shale, and sandstone. These deposits form through the precipitation of zinc-rich minerals from aqueous solutions, often in marine or lacustrine environments where conditions favor the accumulation of metal-bearing sediments. Volcanic deposits, on the other hand, originate from the cooling and solidification of magma or lava enriched with zinc-bearing minerals. Hydrothermal deposits result from the interaction of hot fluids circulating through fractures and pore spaces in rocks, carrying dissolved metals and depositing them as they cool. Metamorphic deposits form through the alteration of pre-existing rocks by heat, pressure, and chemical fluids, resulting in the concentration of zinc minerals within the metamorphosed rock. Various minerals serve as primary sources of zinc in these deposits, with sphalerite, zinc sulfide, being the most common and economically significant. Other zinc minerals include smithsonite, zinc carbonate, hemimorphite, zinc silicate, and zincite, zinc oxide, among others. The concentration and distribution of zinc ore deposits are influenced by geological processes such as tectonic activity, erosion, and sedimentation over geological time scales. Exploration and evaluation of zinc ore deposits involve geological mapping, geophysical surveys, geochemical analysis, and drilling to assess the size, grade, and economic viability of the deposits. Once identified, zinc ore deposits are typically exploited through mining operations, which involve various methods such as open-pit mining, underground mining, and in some cases, solution mining. Extraction techniques depend on factors like the depth, geometry, and characteristics of the deposit. Zinc is a crucial element in numerous industries, including construction, automotive, electronics, and agriculture, where it is used in galvanizing steel, manufacturing alloys, producing batteries, and as a micronutrient in fertilizers. Therefore, the availability of zinc ore deposits plays a critical role in supporting industrial and economic development worldwide. Additionally, as with any mineral extraction activity, the environmental impacts of mining and processing zinc ores must be carefully managed to minimize ecological disruption and ensure sustainable resource utilization. Formation of zinc ore deposits. The formation of zinc ore deposits involves complex geological processes occurring over vast spans of time. These deposits typically originate through a combination of physical, chemical, and biological processes acting on Earth's crust. While the exact mechanisms can vary depending on the specific geological setting, several common processes contribute to the formation of zinc ore deposits. Magmatic processes. Some zinc ore deposits originate from magmatic activity, where molten rock, magma, rich in zinc-bearing minerals rises from Earth's mantle and solidifies underground or erupts onto the surface as lava. As the magma cools and crystallizes, zinc-rich minerals such as sphalerite may precipitate and form veins or disseminations within igneous rocks like granite or diorite. Hydrothermal activity. Hydrothermal processes play a significant role in the formation of many zinc ore deposits. Hot fluids, often derived from magma chambers or deep within the Earth's crust, circulate through fractures and pore spaces in rocks. These fluids dissolve zinc and other metals from surrounding rocks and transport them to cooler, shallower depths where they precipitate out of solution. Hydrothermal fluids can deposit zinc minerals in a variety of geological settings, including veins, breccias, and replacement deposits. Sedimentary deposition. Sedimentary processes can also contribute to the formation of zinc ore deposits. In marine or lacustrine environments, zinc-bearing minerals may accumulate as sedimentary layers or beds over time. This can occur through the direct precipitation of zinc minerals from seawater or through the deposition and subsequent diagenesis of zinc-rich sediments. Common sedimentary zinc minerals include sphalerite, which can form massive ore bodies in carbonate-rich rocks like limestone or dolomite. Metamorphic alteration, metamorphism, the process of changing rocks through heat, pressure, and chemical reactions, can lead to the formation of zinc ore deposits. During metamorphism, pre-existing rocks may undergo mineralogical changes that concentrate zinc and other metals into new minerals or mineral assemblages. Metamorphic zinc deposits often occur in association with rocks like schist, gneiss, or marble, where the original mineralogy has been altered by geological processes. Weathering and secondary enrichment. Weathering processes can alter primary zinc minerals near the Earth's surface, releasing zinc ions into groundwater and surface water systems. These dissolved ions may then be transported and redeposited in secondary enrichment zones, where they accumulate in concentrations higher than those found in the original rock. Secondary enrichment processes can result in the formation of zinc ore deposits in residual soils, alluvial deposits, or as secondary sulfide minerals in oxidized zones of primary deposits. Overall, the formation of zinc ore deposits is a complex interplay of geological, chemical, and physical processes operating over geological time scales. Understanding these processes and their controlling factors is essential for exploring, evaluating, and exploiting zinc resources effectively and sustainably. Properties of zinc ore deposits. Zinc ore deposits exhibit a diverse range of properties, reflecting the variety of geological environments in which they form. These properties influence the exploration, evaluation, and extraction of zinc resources. Below are some key properties of zinc ore deposits. Mineral composition. Zinc ore deposits consist primarily of minerals containing zinc, with sphalerite, zinc sulfide, being the most common and economically significant. Other zinc-bearing minerals include smithsonite, zinc carbonate, hemimorphite, zinc silicate, and zincite, zinc oxide, among others. The mineral composition of a deposit influences its physical and chemical characteristics, as well as its processing requirements. Ore grade. The grade of a zinc ore deposit refers to the concentration of zinc, usually expressed as a percentage or parts per million, within the ore body. Higher grade deposits contain more zinc per unit volume of ore, making them more economically viable for extraction. Ore grade varies widely among different deposits and even within the same deposit, affecting the profitability and feasibility of mining operations. Deposit size and geometry. Zinc ore deposits vary in size and shape, ranging from small, localized occurrences to large, extensive ore bodies. Deposits may occur as veins, lenses, stratabound layers, disseminations, or stockworks within host rocks. The size and geometry of a deposit influence mining methods, infrastructure requirements, and overall resource potential. Host rock characteristics. Zinc ore deposits are typically hosted within specific rock types, including sedimentary, volcanic, hydrothermal, and metamorphic rocks. The composition, structure, and texture of the host rocks can affect the distribution, concentration, and accessibility of zinc minerals. Understanding the properties of host rocks is essential for targeting exploration efforts and optimizing ore extraction. Structural controls. Structural features such as faults, fractures, folds, and shear zones play a crucial role in the formation and localization of zinc ore deposits. These structural controls influence the migration of hydrothermal fluids, the deposition of zinc minerals, and the overall geometry of the deposit. Detailed structural analysis is often necessary to interpret the spatial distribution and orientation of ore bodies. Mineralogy and textures. The mineralogy and textures of zinc ore deposits provide valuable insights into their origin, history, and potential for economic exploitation. Detailed mineralogical studies can identify ore minerals, gangue minerals, and alteration assemblages, aiding in ore characterization and processing optimization. Textural features such as grain size, shape, and distribution can also affect ore processing efficiency. Associated metals and minerals. Zinc ore deposits may contain other economically valuable metals and minerals in addition to zinc. Common associated metals include lead, copper, silver, and cadmium, while gangue minerals such as quartz, calcite, and dolomite are also frequently present. The presence of associated metals and minerals can impact ore processing strategies, recovery rates, and marketability. Weathering and alteration. Weathering processes can alter the composition and properties of zinc ore deposits near the Earth's surface, leading to the formation of secondary minerals and enrichment zones. Understanding the extent and nature of weathering and alteration is essential for evaluating the economic potential and environmental implications of a deposit. Overall, the properties of zinc ore deposits are highly variable and dependent on factors such as geological setting, mineralogy, grade, and structural controls. A comprehensive understanding of these properties is essential for effective exploration, development, and management of zinc resources. Minerals of zinc ore deposits. Zinc ore deposits contain a variety of minerals that serve as primary sources of zinc, as well as associated minerals that may contribute to the overall mineralization. Understanding the mineralogy of zinc ore deposits is crucial for exploration, mining, and processing operations. Here's a more detailed look at some of the key minerals found in zinc ore deposits. Sphalerite. Zinc sulfide sphalerite is the primary ore mineral for zinc, accounting for the majority of zinc production worldwide. It typically occurs as a dark-colored mineral with variable transparency and can exhibit a wide range of colors due to impurities. Sphalerite often forms well-defined crystals but can also occur as granular masses or disseminations within host rocks. Its high zinc content and relative abundance make sphalerite the main target for zinc extraction. Smithsonite. Zinc carbonate. Smithsonite is a secondary zinc mineral that forms through the weathering and alteration of primary zinc sulfide minerals like sphalerite. It commonly occurs as botryoidal or stalactitic masses, nodules, or crusts with colors ranging from white and gray to green, blue, or pink. Smithsonite is less common than sphalerite but can still be an important source of zinc in certain deposits. Hemimorphite. Zinc silicate. Hemimorphite is another secondary zinc mineral formed by the weathering and alteration of primary zinc sulfides. It typically occurs as botryoidal or crystalline masses with colors ranging from white and colorless to blue, green, or yellow. Hemimorphite may contain significant amounts of zinc and is sometimes mined as a zinc ore, particularly in oxidized zones of zinc deposits. Zincite. Zinc oxide. Zincite is a rare mineral composed of zinc oxide, ZnO, and may occur as bright orange to red crystals or granular masses. While zincite is not a common primary ore mineral, it can occur as a secondary mineral in oxidized zones of zinc deposits, resulting from the weathering and alteration of primary zinc sulfides. Galena. Lead sulfide. Galena is a common associated mineral found in many zinc ore deposits, often occurring as gray metallic crystals or masses. While galena is primarily a lead ore mineral, it may contain significant amounts of zinc as an impurity, particularly in zinc lead sulfide ores. Separating galena from zinc ores is important for optimizing zinc recovery during processing. Chalcopyrite. Copper iron sulfide. Chalcopyrite is a copper ore mineral that occasionally occurs alongside zinc ores, particularly in polymetallic deposits. It typically appears as brassy yellow crystals or masses and may contain minor amounts of zinc. The presence of chalcopyrite can influence processing strategies and metal recovery rates in zinc ore deposits. Pyrite. Iron sulfide. Pyrite is a common sulfide mineral that may occur as an accessory mineral in zinc ore deposits. It forms shiny, metallic crystals or masses with a brassy yellow color and is often associated with sphalerite and other sulfide minerals. While pyrite itself is not a significant source of zinc, its presence can affect ore processing and metallurgical performance. Gangue minerals. In addition to zinc-bearing minerals, zinc ore deposits may contain various gangue minerals that accompany the ore minerals. Common gangue minerals include quartz, calcite, dolomite, and barite, among others. Gangue minerals may influence the physical and chemical properties of the ore, as well as the efficiency of ore processing operations. Understanding the mineralogy of zinc ore deposits is essential for assessing their economic potential, designing extraction methods, and optimizing mineral processing techniques. Detailed mineralogical studies help characterize ore bodies, identify mineral associations, and develop strategies for maximizing zinc recovery and value.